Assalamu alaikum dear students, I hope you all are fine and in the best conditions of your health. So in today's lecture for the course of organic reaction mechanism, we shall study about the concept of stereoselectivity. So this is part 2 of the stereoselectivity. In the previous lecture we have studied about the terms of selectivity, specificity, then we saw about the prochirality, the homochirality, enantio-selectivity, enantiotopic, diastereotopic, and we also saw about the rephases and the psi phases of the carbonyl system and the imine system. So the key concepts of this lecture will be, again we shall have some revision of selectivity, specificity, we shall see about what do we mean by stereoselectivity, and the most important concept which we shall discuss in this lecture will be the type of stereoselectivity. So selectivity is what things whenever you are considering a reaction and the reaction is resulting in formation of two products while one of the two products is dominating, right? So if there is preference of a reaction mechanism to favor formation of a one product over other, so this is called preference or selectivity, right? Similarly, if you are getting one product from two different reactants but one of the reactant is reacting faster, right? So you have two reactions, but you have reaction A and you have reaction B, and both of these reactions is resulting in formation of the same product, but one reaction is occurring at a faster rate while the other is occurring at a slower rate, right? So it means that a particular reaction pathway is favored, right? So whenever there is the concept of preference or whenever there is a concept of favoring one product or favoring one reaction route, this is the concept of selectivity. While what about specificity is that if there is no other option available, if there is only one option, only one product can be formed, only one reaction route can be favored, then in that case this is the concept of specificity, right? So specificity occurs if there is no other option, selectivity occurs when there is option available but one of the two options is more preferred, right? So when we are considering the reactions or the reactants involving the stereo isomers, then the selectivity will be considered as stereoselectivity, right? So we also saw in the previous lecture that the selectivity is of three types: chemoselectivity, regioselectivity, and the stereoselectivity. So chemoselectivity refers to if you have two functional groups or more than two functional groups, then which of the two functional groups will react in preference, right? So which of the functional group will preferentially react? This is known as chemoselectivity. So chemoselectivity is related to the functional groups. Then we have regioselectivity. So regioselectivity means that if you have two or more than two site of action available, so if a reaction can occur at two or more than two positions but the reaction preferentially occur at one position, right? So since this is preference in position, so this is called regioselectivity. So the word of regio is from region means place, right? So if a particular position, if a particular place of your molecule is being preferred to be reacted on, then this is concept of regioselectivity. Then we have stereoselectivity, which is our topic. So stereoselectivity means that which of the two isomers is being formed at a in more amount, or which of the two isomers is reacting at a faster rate. So both of these terms will be considered in stereoselectivity, right? Specificity means there is no other option and your reactant is completely determining what is being formed or which of the two isomers will react faster. Again, we have this concept that considering that which of the reaction will be stereoselective or which of them will be not stereoselective, right? So consider that we have two reactants A and B and they are forming two different products. So whenever you are getting two different products, it means that A and B have two possible reaction routes. So one of the possible reaction route or one of the possible mechanism is formation of C, while the other possible mechanism is formation of D. But since C is forming as a major product, it means this reaction route has preference. So the reaction mechanism that is involving formation of C, that has more preference. So this is more selective, since the reactant or the product is a stereoisomer, so such reaction will be considered as a stereoselective reaction because it is preferring the formation of one of the stereoisomers. Again, in another reaction, suppose that we have two reactants, they can be chiral or they cannot be chiral, right? So both options are existing. Suppose that these are also forming two products, C and D, but if the products are formed in equal amount, it means that this root and this root both are favoring to equal extent, so there is no preference because both are equally preferred, right? So there is no selectivity, there is no preference, there is no favoring of one over the other. Such a type of reaction will be considered as non-stereoselective reaction, right? So stereoselectivity can be described as a process in which different reactions occur at different rate to form same product. So if you have the product which is same but the reactions are different, right? For example, we have A and B as reactant and we have E and G as reactant, so they are forming the same product. So E and G form C and D, A and B form C and D, but there is a difference in reaction rate. Suppose that A and B react faster to form C and D while E and G takes longer time. So since A and B is reacting faster, it means this reaction has preference, right? So this reaction will be selective. So in case if your product or reactant or both are stereoisomers, then such a reaction will be considered as stereoselective reaction. On the other hand, if the two reactants A and B and E and G, they separately convert into C and D, but the reaction rates are equal. So A and B and E and G both react at equal rates to form C and D. So this will be considered as a non-selective reaction because there is no preference, there is no selectivity. So both of the reaction routes are of equal importance, right? So there is no preference, there is no selectivity, so such a type of reaction will be considered as non-stereoselective reaction. However, when there is no other option, if A and B is the only option to get C and D and E and G is not reacting at all, so this will be considered as 100% selective, right? So 100% selectivity is called stereospecificity, right? So stereospecificity occurs when there is no other option. Stereoselectivity always occurs when there is an option, right? When you have more than one option and one of the option has preference, while stereospecificity occurs when you don't have any other option, right? So let's consider about some reactions that are enantio-selective and some reactions that are diastereoselective, right? So whenever a reaction is enantio-selective, it means that it will form two enantiomers, but one of the enantiomer will be formed in larger amount, right? Suppose we have this molecule, you can see this in allyl alcohol, and what we are doing is we are carrying out the epoxidation of this molecule, right? So how we can say epoxidation? Because we are using this tertiary butanol peroxide, right? Tertiary butyl peroxide. So this tertiary butyl peroxide is since that's the peroxide, so peroxide, when they react with alkene, they carry out the epoxidation of the alkene. So we can have two isomers, one in which the epoxide is forming on the above surface and other in which the epoxide is approaching from the below face, right? So this isomer, you can see here, you are getting 95% enantiomeric excess. So the other isomer will be formed in 5% enantiomeric excess, right? So that other isomer will be considered as recessive because it's forming only in 5% enantiomeric excess, while the enantiomeric excess of this isomer is 95%, right? So that other isomer will be considered as recessive. So what is this molecule? So this molecule is actually a chiral reagent, and this chiral reagent will ensure that the epoxidation occurs on the above surface, right? So this is an example of an enantio-selective reaction in which we are using a chiral reagent, and this chiral reagent is helping to form one of the enantiomer in excess. So if you are not using this reagent or if you are not using this substrate, then in that case both of the isomers will be formed in equal amount. The reaction will be non-selective when you are not using this molecule, right? But when you are using this molecule, then you get enantiomeric excess of 95% for this enantiomer, right? So our reactant is achiral, but we are getting an enantiomer here, so we are getting two enantiomers, one this one and the other in which the epoxide is below the plane. But since one of the isomer is being formed in excess, so that's why, since the enantiomer, one of the enantiomer is forming in excess, therefore this reaction will be considered as enantio-selective. And as we have already mentioned, that enantio-selective reactions are also called asymmetric synthesis, right? And normally when you are carrying out the asymmetric synthesis, we may use chiral catalyst or we may use chiral auxiliaries. So these reagents, they help to preferentially convert the reactant into preferentially one of the two isomers. Another enantio-selective reaction here we have. So this is a molecule. You can see that we can carry out the aldol condensation. So just for note, please write a carbonyl here because the carbonyl is missing here, right? So that's a mistake. So just put a carbonyl here. Right, so here we have a carbonyl group, we have an oxygen here, right? So here we have carbonyl, this carbonyl is missing. So this is simply an aldol condensation. So here you can see this enolate that will be formed, that will attack on this carbon, and we'll get a hydroxyl group here, and followed by the elimination of water. So we'll get a carbon-carbon double bond between this carbon, which was previously this one, and this carbon here. So you're getting carbon-carbon double bond by means of aldol condensation here, right? So what we are using is that we are using a chiral catalyst, and the chiral catalyst is S-proline. So proline is an amino acid, and we are using the S isomer of this proline. So this proline is a chiral catalyst. So what happens that when we are using S-proline as a chiral catalyst, so the reaction results in formation of an enantiomer, right? So one enantiomer is this one, and the other enantiomer is this one. So whenever you have confusion whether that this is an enantiomer or diastereomer, you can easily use one tip. If your molecule has only one chiral center, then that will be an enantiomer, right? So whenever you have confusion and you are feeling difficult to decide whether that is an enantiomer or a diastereomer, just remember that if you have only one chiral center, then this molecule will definitely be an enantiomer. While if you have two chiral centers, then it is safe to say that the molecule will be a diastereomer, right? So the basic definition for enantiomer is that the enantiomers are isomers which are mirror images of each other, and the mirror images are non-superimposable, right? The enantiomers are non-superimposable mirror images of each other, while diastereomers are molecules which are not mirror images, right? So whenever you have only one chiral center, be sure that this will be an enantiomer. But if you have two chiral center or more than two chiral centers, then it is safer to say that a molecule will be a diastereomer, right? So this molecule does not have a chiral center. So it had a chiral center here, right? But the stereochemistry of the chiral center is not defined, right? So this is a racemic molecule because there is no enantiomeric excess at present. But when we carry out the aldol condensation of this reaction in presence of chiral catalyst, what happens that we get two enantiomers here. Why we are saying enantiomer? Because there is only one chiral center here. But this isomer, this A isomer, it is formed in much larger excess. So the enantiomeric excess of A will be higher than B, right? So since that's forming in more preference, that's why, since the reaction is favoring the formation of one enantiomer, so this reaction will be considered as an enantio-selective reaction or the asymmetric synthesis. Now we'll consider an example of diastereoselective reaction, right? So in a diastereoselective reaction, we get two diastereomers, while one of the diastereomer will be formed in preference, right? So here it is important that when you are considering a diastereoselective reaction, then in that case it's normally common that you are starting with an enantiomer, right? So the reactant has one chiral center, and in the reaction you are going to generate another chiral center. So you can see here in this example, so we are already having a chiral center here, right? So chiral centers, as you know, they are designated by asterisk. So whenever you see a star on a carbon, so that is indicating that this center is a chiral center here. So more stars on a molecule means it has more chiral centers. So this center is a chiral center, and you know that this is a carbonyl, and there are two groups attached to the carbonyl which are different. So it has two faces. One will be re face, another will be psi face. So if you are seeing it from above, just like I'm seeing here, so you can just designate it. So just assign designation of 1 to oxygen, 2 to this group, 3 to this group. So if you go on from like that, so this is clockwise. So this phase is a re phase, while the other phase that will be below, that will be the psi phase right here. So what happens that we have a reagent and we are going to carry out the addition of hydrogen cyanide. So the hydrogen will go to this oxygen and the cyanide will go to the carbon. So there are two options. The cyanide can approach from the re phase, that means from above, or it can approach from the psi phase, that means from below, right? So depending on if it approaches from above or it approaches from below, so we get two isomers right here. So this is chiral center, and we had already existing chiral centers. So since the product has two chiral centers, we can see that the two isomers, they are diastereomer, right? So that's a diastereomer, that's also a diastereomer. How we can say that are diastereomer? Because they are not mirror images of each other, right? So suppose that this isomer, this diastereomer is forming in excess, right? So diastereoselective is a reaction in which you get two diastereomers, and one of the diastereomer is forming in preference, is forming in excess. So whenever there is preference, there is selectivity, and here the selectivity is in terms of diastereoselective reaction, right? So this reaction will be considered as a diastereoselective reaction. And why it's diastereoselective reaction? Because the carbonyl group, it has two faces. The carbonyl group in this specific case, this is diastereotopic, right? So if a carbonyl can give you an enantiomer, so carbonyl will be considered as enantiotopic. But this carbonyl group, it has already one chiral center, and when we carry out reaction on this carbonyl, we'll get another center. It means this carbonyl can give you a diastereomer, right? So it means this carbonyl group is diastereotopic, right? So that's the prochiral center, because it will result in formation of another center, and since this carbonyl will result in a diastereomer, therefore this carbonyl is considered as diastereotopic, and the reaction is diastereoselective reaction, because the two diastereomers that are formed in the reaction, so one of the diastereomer is forming in excess. Another example of the diastereoselectivity here. So here we have an achiral 4-tertiary-butyl cyclohexanone. So you might wonder why we are saying it as achiral. Why? Because the reason is that this carbon, it has a tertiary-butyl group attached, hydrogen attached, and the two groups are same, right? So that's a prochiral center, right? Why? Because if I just bring out replace one of these two CH2 groups with something else, it will become a chiral center, but at present it's not a chiral center, right? So this molecule is an achiral molecule, and it has also the plane of symmetry, right? So what we do is that we have carbonyl system. So this carbonyl has two faces, the above face and the below face right here. So hydride, if I carry out the addition of the hydride, so this hydride can either approach from below, from the axial position, or from the equatorial position. So if hydrogen is approaching from above, so that position will be axial here, right? And if this hydride is approaching from below, then the position will be equatorial position, right? So here we have the hydride that is approaching from the axial position, and here we have a hydride that is approaching from the equatorial position. So from the basic stereochemistry from the previous semester, you know that the bulkier group should be at the equatorial position, because if the bulkier group is at axial position, then there are some diaxial interactions. So here we have hydrogens that are at axial position, hydrogen at axial position. So these axial hydrogens will will result in the steric hindrance with this bulkier group, that is axial position, right? So whenever we are getting two products, then the product that has a bulkier group at the equatorial position, that is more favored, right? So when the hydride is added on this carbonyl system, we get two isomers, the trans isomer and the cis isomer. The trans isomer, why we are saying it's trans, because this hydroxyl is below and this tertiary-butyl group is above, right? So since these two groups are on opposite side, one is below, one is above, so this is the trans isomer, while this isomer in which this group is above, this group is also above, so both groups are above, right? This is cis isomer here. So this trans isomer will be formed in preference. Why formed in preference? The reason is that, so we have a hydroxyl group at axial position in cis, which is not preferred, but the hydroxyl group at equatorial position, so this is a more stable conformation right here. So this diastereomer will be formed in excess, right? So this reaction is an example of diastereoselective reaction, and the diastereoselectivity is arising from the carbonyl group. So this carbonyl is diastereotopic because the addition of hydride to this group will result in formation of a diastereomer. Right. Now we have the type of stereoselectivity. We have so far discussed about the enantio-selectivity, in which one enantiomer is forming in excess. Then we had the diastereoselectivity, in which there is possibility of formation of two isomers, two diastereomers, but one of the diastereomer is formed in excess. Now we have types of stereoselectivity. So there are three types of stereoselectivity: the product stereoselectivity, the substrate stereoselectivity, and the substrate product stereoselectivity. We shall discuss each term briefly. So firstly, we have product stereoselectivity, right? So whenever we have one substrate, right, so one reactant, and one reactant is forming two different products, right, but the formation of one product is favored over the formation of other product, right? So this preference may be in the form of difference in amount. So maybe you can say the product 1 is formed in higher amount while product 2 is forming in lower amount, or this difference can be in the form of rate of reaction. So this substrate that is forming product 1 and product 2 at different rates, so maybe the formation of product 1 is occurring at a faster rate, right? So it means that this is selectivity and the reaction is preferring the formation of product 1. So this is selectivity, but the selectivity is only depending on the product. It's not depending on the substrate, because substrate is same and we are getting two products, right? So if a substrate results in formation of two different products at different rates, then such type of stereoselectivity is called product selectivity, because the selectivity is only depending on the product. Also, if one of the products is forming in larger amount than the other, then such reaction will be also considered as product selectivity, right? So the selectivity in the product or the product selectivity is dependent on the rate of reaction as well as amount of product formed, right? So suppose that K1 and K2 are same, but one product is formed more than the other, then this will be considered as product stereoselectivity. If the amounts are same but the rate of formation is different, then in that case again this will be example of product stereoselectivity. The next type of selectivity is the substrate stereoselectivity. It means that you have two different substrates, and these two different substrates form the same product, but they are forming the same product at different rate. For example, this reagent or this substrate is forming product at K1, while this substrate 2 is also forming the same product, but you can see the rate of formation of product from substrate 1, that's K1. So K1 is very higher than K2. So here in this specific case, the rate of reaction for this reaction is much higher. It means this reaction is stereoselective, but the stereoselectivity here is depending on the substrate, right? So when the selectivity is depending on the substrate, such type of stereoselectivity is known as substrate stereoselectivity. So in the previous slide we saw about the product stereoselectivity, because the selectivity was dependent on the product, while the substrate stereoselectivity is a selectivity in which the selectivity is totally depending on the substrate because we are getting only one product. However, the substrates are different. So substrates are reacting at different rates. So the substrate which is reacting at faster rate, we say that is more preferred than the substrate which is reacting at a slow rate. Now the third type of selectivity is called the substrate product stereoselectivity. Right? As the name suggests, so here the stereoselectivity will be depending on the substrate as well as product. Right? So if you want to define the substrate selectivity in that case, so in that case, if two different stereoisomers of a substrate result in formation of different product in different amount and at different reaction rates, then such type of stereoselectivity is called substrate product stereoselectivity. So consider that these are two stereoisomers, so AB and BA. So there are two stereoisomers, they are different stereoisomers right here. So this isomer result in formation of a product which is CD, while the other isomer result in formation of a different product. Now you have the stereoisomers, and the stereoisomers are resulting in formation of different products, and the products are forming in different amount and the reaction rate is also different. So here selectivity, that which of the product will be formed in more amount or which of the reaction will occur at a faster rate, that is depending on your reactant, and it is also depending on your product right here. So in this specific case, since the products are different and your stereoisomers are different, the rate of reaction are different, the amount formed are different, so there is preference, for example, that maybe that D is forming at a much faster rate and in a larger amount, but which will be formed in larger amount or which reaction will occur faster. So this is depending on the product, and this is also dependent on the substrate. So such stereoselectivity which is dependent on the substrate as well as product, such stereoselectivity is called substrate product selectivity. Right. So in this lecture we have studied about the stereoselectivity, then we have studied about stereospecificity. So the difference between selectivity and specificity is that whenever you have an option, more than one option, and one of the options is preferred, then this is called selectivity. But when you don't have any option, then in that case this is case of specificity. We also studied that 100% stereoselectivity is called stereospecificity. Right? Then we considered about the enantio-selective reaction, that if a reaction results in formation of two enantiomers, of which one enantiomer is more dominant or is formed in larger amount or it is formed at a larger reaction rate, then this is called enantio-selective reaction. While if a reaction results in formation of two diastereomers, of which one of the diastereomers is formed at a larger amount or at a faster reaction rate, then this is called diastereoselectivity. We also studied about the enantiotopic and diastereotopic. Right, so if a carbonyl carbon of any group, it is not chiral, but adding a group on it will convert it into chiral center. So if this chiral center is part of an enantiomer, then this carbonyl will be considered as enantiotopic, and if this carbonyl is a part of a diastereomer, if that results in formation of a diastereomer, then this carbonyl will be considered as diastereotopic. So lastly, we considered about type of selectivity. We saw about the product stereoselectivity. So if the stereoselectivity is determined by the product, right? So simple way is that if we are using one substrate and the one substrate is forming two products at a different rate or in different amount, since the stereoselectivity is depending on the product, so this is example of product stereoselectivity. So if you are getting same product from two substrates, then in that case, since the selectivity is depending on the reactant, then such type of stereoselectivity is called substrate selectivity. While if the stereoselectivity is depending on both your reagent as well as product, then in that case such type of stereoselectivity is called substrate product stereoselectivity. So that's all for today's lecture. I suppose you have understood it well. Thanks for your attention.